Okay, we're going to look at some expected value problems. So we have a charity fundraiser that is got a spinner, and it says a donation of $2 required to play the game. For each $2 donation, the player spins it once to receive the amount of money indicated in the sector that lands on the wheel. The spinner has an equal probability landing on all 10 sectors. Represent the net contribution to the charity when a player plays the game once. So, okay. So it's kind of nice because they have it all set up for us. But so I'm gonna copy what they have here. They call X. They're calling X the net deal, net contribution. So this is the person pays $2, so the charity gets $2, and here the charity gets $1, and at the end here, the charity loses $8. So that's our probability, and that's the P of X. So we have to figure that out. So there's 10 spinners, and I'm looking at this, and this means that the person gets $0. So that's 1, 2, 3, 4, 5, 6. So that's 6 out of 10. So that's 0.6 with the probability. So there's a 60% chance that the charity is going to make $2 on it. And then let's see, $1. They make $1 if it lands on here. So $1. 1, 2, 3. So this is 0.3, and then they lose $8 if the spinner lands here. So this is 0.1. So this is a probability distribution. It's got all the different possibilities and the probability associated with it. So that's what's called a probability distribution or a probability model. We can say that. And as long as these add up to 1, if we add these up, we know that we have everything covered. So we do. So that's a good way to check the probability model. If it ever says verify the probability model is correct, we just sum the probabilities and we show that they're equal to 1. And now we know that it's a complete probability model. And then part B says, what's the expected value? So the expected value for X, which would be the mean X that we would expect. Okay, so if we play this play it lots and lots of times, the mean value that X would take on, the mean take. So this would be the mean donation. So 60% of the time they get $2. So 60% of the time they're going to get $2, plus 30% of the time they're going to get $1, plus 10% of the time they're going to get $8. So remember, the expected value is just the sum of the probability times the outcome, or times the result. So this is going to be 0.12 plus 0.3 plus 0.8. So that means that if we played this over and over and over again, the mean contribution would be, let's see. Oh, sorry, this is 1.2. 1.2. 1.2 plus 0.8 is $2. No. Yeah, that's right. 1.2 plus 0.3 is 1.5. Oh, this is negative. So this is negative 1.5. And then minus 0.8 is 0.7. Is that right? Just take a minute and make sure I got that right. Yes, 0.7. So that means that the place is going, or the charity is going to average $0.7 or 70 cents per play of this game per person that plays. And then it says the charity would like to receive a net contribution of $500 from this game. What is the fewest number of times a game must be played for the expected value of the net contribution to be at least $500? So, well, it's 70 cents per play. Okay, 70 cents per play. So the expected value, if I want this to happen, I want this to be $500. So how many 0.7s would I have to put in to come up with $500? So 0.7 times how many number of plays to get to 500. Okay, so if I divide that across there, if I divide by 0.7, I'm going to multiply both sides, the top and the bottom, by 10. So that's going to get up to 5,000. And 5,000 divided by 7 is, let's see, this is 7, and then that's 10 left over. So it's going to fit in there 1. And then that's 30 left over, and that's going to be 4, and then plus a little bit more. So there's some remainder after that. So 714 won't get me to 500, so 715 plays. So just divide that. So you would have to have 715 plays to have the expected value be, be 500, at least 500. Okay, it went actually a little bit more than 500, but we didn't want it. 714 wouldn't get us there. And then it says, based on last year's event, the charity anticipates that the Spin the Pointer game will be played 1,000 times. The charity would like to know the probability of obtaining a net contribution of at least 500 in 1,000 plays. The mean and standard deviation for the contribution of the charity of 1,000 plays of the game are $700 and 92.79, respectively. Use the normal distribution to approximate the probability that the charity would obtain a net contribution of 500. Okay. So then what they're saying is that normal distribution, and it's normal distribution, this is 500 plays, and they're saying that, 1,000 plays, and they're saying that the mean, if you did this a bunch of times, a bunch of 1,000 plays, if you hosted a bunch of galas and you had 1,000 plays at each one, the mean contribution would be 700, and the standard deviation would be $92. So 92.72. 92.79, 0.79. Okay, so that makes sense. And then it says, use the normal distribution to approximate the probability of charity obtain a net contribution of at least $500 in 1,000 plays of the game. So $500 would be somewhere over here, way on the low side. $500 and at least 500 would be this probability. So I would draw this picture to help you out. So now I got to figure out what that z-score is. So that z-score is 500 minus 700 divided by 92.79. And so that's going to be equal to negative 200 divided by 92.79. And the probability that we'd get a net contribution that's greater than or equal to 500 will be equal to the probability of getting a z-score that's greater than negative 200 divided by 92.79, which we have to go to a normal calculator again here. You can do your normal CDF with either set it at 500, then set your mean and your standard deviation to be what it's supposed to be, 92.79. Looks like you're getting a little bit of a glare there. And then put that there, or you can get the z-score and leave your mean and your standard deviation at 0 and 1. So I'm just going to go to a normal calculator real quick. Normal distribution calculator. I always do that one. Let's do a different one. I've shown you that one a bunch of times. let's do the normal calculator. And and let's do the one from StatTrak and see how that does. Okay, the standard score. Oh, I don't know that. This one needs you to do that. So let's get out the calculator and do that. So this one is not as good a one, I would say right away. So my normal calculator was negative 200 divided by 92.79. So I have a z-score of negative 2.1554, negative 2.1554, negative 2.1554, and I want the cumulative probability, and this is going to say that's less than that z-score. And, I guess I could have put the number in and we could have got those two pieces there. So I'm going to calculate. So 0.016. So what that one told me, since it's the less side, this calculator told me this is 0.016 sitting here. So then I have to take 1 minus that. So that's going to be 0.984. So 0.984. So that's going to be the probability. Well, I already have that there. The probability of net contribution is greater than 500 is going to be 0.984 in that situation. Looks like on this one I could have also, we're going to delete that out there, and I'm going to put this at 500, and I want the mean was 700, and the standard deviation was 92.79. And I'm going to calculate, just to make sure I got this right here, 0.016 again, but again, that's below. So the other calculation was always, the other calculator was a lot better. The StatTrak one was not as good. I like this one better. So if you go to it, it actually even gives you the picture and everything. So I'm going to say the mean is 200. The standard deviation is 92.79. And I want above, the probability above, and I want the probability above 500. And I'm going to hit enter. And wait a minute. Oh, the mean was 700, not 200, sorry. And I'm going to hit enter. And there you go. There's even a picture of it. It's all this stuff here. And 9844, is that what I said? 9844. 9844. All right, good. So there is the end of that video. And I'm going to pause. All right.